regenerative braking systems for electric vehicles to be delivered by our esteemed expert speaker, Dr. Dipankar Dev. Before we proceed with this session, let us have a brief introduction of our expert speaker. Dr. Dipankar Dev is a full-time professor at the Center for AI and Robotics, Indian Institute of Technology, Mandi, with over 2 decades of experience spanning academia, industry, and innovation leadership. He holds a PhD in electrical engineering from the University of Virginia, USA 2007, and has worked in advanced R&D roles in United States and India, including at GE Global Research and Baron Associates, before joining the IIT system, including a couple of years at IIT Guwahati. Professor Dev had published more than 60 SCI indexed journal articles, authored or edited 12 books with leading international publishers, and holds a total of 18 granted patents in India and United States, and has also taught courses on IP and ideation through design thinking. His research focuses on adaptive and nonlinear control, aerial robotics, machine learning applications, and renewable energy systems, with several technologies translated into patented deployable solutions for deep tech, med tech, sustainability, and rural impact. He has presented his work at premier control conferences such as ACC and CDC, and is consistently ranked among the top 2% researchers worldwide by Stanford elsewhere. A senior member of IEEE and fellow of IE and IETE, Professor Deb has played a pivotal role in shaping innovation ecosystems as director, incubation of IIT Mandi Catalyst, leading large-scale incubation, policy drafting, CSR initiatives, and nationally funded programs in entrepreneurship, education, and deep tech development. So we are very grateful to have such an eminent personality among us. So now I request Dr. Dev sir to start with his session. Thank you.
Thank you. Thank you so much for these kind words. So my talk is on a hybrid system. It is applicable. These concepts are applicable in electric vehicles, but for ease of understanding of all concerned, I'm taking a topic which is having hybrid concept, hybridization concept, but it is not on electric vehicles. There will be battery modeling involved in this, but how we can optimally utilize some renewable sources while applying machine learning techniques to do something called as forecasting, and do it using a good estimate of the battery life. This is what will be the talk for today. It will be applied in hybrid farms, because hybrid wind farms, because the wind turbines which make up these wind farms are associated with a battery energy storage system. Each wind turbine will have a battery energy storage system. And so this is the hybrid wind farm. But these hybrid wind farms are getting what? Are getting free stream velocity or the wind speed as the input. But because wind is random, so the power generated from a wind farm or wind turbine, each of the wind turbine, the power generated from them will be random. But if you randomly generate any amount of power from a given source, and you do not know what it will be, or you cannot predict what the power generation capability of each of these turbines will be at a future time, then it is of not of much use, because you cannot promise, or you cannot give that power or deliver it to a utility based on simply the randomly generated power. So what you have to do, you have to use some battery storage systems which will supply the shortfall or store the surplus. But if you do that with because wind is highly random in nature, highly stochastic in nature, and so if you do that in every time period, or let's say for example in wind forecasting it is called short term wind forecasting. So every 10 minutes there is something called as dispatch window. I will be getting into, I will be defining all of these terms that I am using right now. So if right now it is 6:10 p.m. If at 6:10 p.m. I have a certain wind speed, I have to predict ahead of time that what will be the wind speed or the power generated from the wind turbine, which is equivalent to the, because there is a cubic formula. So I will know what is the power generated if I know the wind speed, but I will not know accurately the wind speed, right? It is random. So at now it is 6:11. So at 6:11, if I am predicting what will be the wind speed at 6:21, let's say 10 minutes ahead of time, then what I can do is when actually it becomes 6:21, I will compare what is the wind speed that I predicted and what is the wind speed right now. And I can find the error. And using error statistics like root mean square error or mean absolute error and some of these other things, I can try to minimize this error. If I have advanced machine learning algorithms, I will be able to minimize such error. But if I use charging and discharging of the battery too much, because wind is random, so it may be 5 meter per second right now, 10 minutes later it can be 12 meter per second, and another 10 minutes later it may be 4 meter per second. So it can change very fast. So it will mean that every dispatch window I may have to charge, then discharge, charge, then discharge my battery. If I keep doing that very often, then my battery life will be gone very soon. And in such scenario, it will not be very cost effective. So the whole idea in this machine intelligence forecasting for hybrid wind farms is how I can predict what will be the accurate, what will be the, or how I can be as close as prediction as the actual wind speed, how I can predict the estimation, and then it should turn out to be as close as the actual one, right? So that the error is less. This is the goal. So, but I should not, was there a question?
Sir, will you please reshare your PPTs?
Oh, it is
Your
not.
presentation is not visible. You have to reshare it.
Okay. Now is it visible now?
Hi, yes, sir.
Yes, sir. Yes.
Okay, okay. Anyways, I was on the first slide only because I wanted to explain each of the terms. But if at all at any time, say I'm not very, I always use Google Meet for all the online presentations I do. I'm not very much
Okay.
comfortable or very conversant with much of Teams. So if at all at any time the presentation goes away or gets stuck, doesn't move, please let me know. Don't hesitate. Okay, so this is my humble request.
Okay, sir.
Yes, sir. Yes.
At any
Okay.
time it happens, anyone, please let me know. So I was at the first slide, so there nothing is lost here. Because I'm trying to explain each of the terminologies over here. So the goal is to use batteries to supplement what is random. So wind speed is random. So to cover for that, we are using batteries. But if we always use the batteries in every 10 minutes, and whenever there is something called as ramp event means when the wind speed drastically reduces in a very short time or drastically increases in a very short time. In that case, my charging or discharging of the battery will be by a large amount, and that will diminish the battery life. And so we don't want to use the battery too much, more than what is required. And I will show you with concrete data why using battery very carelessly is not a good idea. So we must have very good machine intelligent or machine learning algorithm which will reduce this error so that battery usage will be less. I will also be talking about other techniques like multi-criteria decision making or and wind wake management of the wind turbines so that the battery life is managed. This this multi-criteria usage and optimization algorithm that is being used over here is applicable in any application of batteries where where you want to do optimally, you want to use the batteries. This technique is applicable, and so this is applicable or useful to anyone working with batteries in anything like regenerative braking or any hybrid electric vehicles or any such methods. I will be also talking about battery models where this impacts, but our focus for this talk will be to come to identify the sweet spot where the optimal usage takes place. So with that background, I am going ahead with the overview for this talk for today. So primarily, I'm talking about hybrid wind farms as a concept. What are the challenges in hybrid wind farms? I'll talk about decision making, forecasting, and life in enhancement of battery energy storage systems. These three things. So I have three objectives in this talk. Objective one is how to do forecasting for hybrid wind farms. Objective two, how to do better decision making in hybrid wind farms. And objective three, how to enhance the life of the battery energy storage systems in hybrid wind farms. And when I have done these three things, I will have an integrated solution for the hybrid wind farms. Okay. So this whole thing is the genesis of this whole thing is in a US patent that we filed in the year 2014. I was working at GE Global Research at that time. And this filed patent that was filed in 2014 was granted in September 4, 2018. And this is really the genesis or the root problem that we identified over there and solved it. And this has formed the core of wind farm research that I then continued to do through multiple PhD students uh, over the next 4 to 5 years and still continue to do. So this diagram will explain the very simple concept. It is not difficult, and I lecture quite often on patenting. And if you understand this slide, you can understand that doing a patent, filing a patent or getting a granted patent, if you can think of fundamental problems, is not very difficult. Rather, it is very simple and easy. So I would like you to look at here, look at in this block diagram. There are two wind farms. Okay, these cylindrical shapes are representing wind farms. So there may be so many wind turbines here. Okay, so many wind turbines here. They are wind farms which are located nearby. Nearby in the context of wind farm means like 100 miles or so. Okay, they are connected to the same grid, same utility grid. In India, we have national grid. So can have a wind farm in Gujarat. We can have a wind farm in Tirupati and a wind farm in Jagannath Puri, and they can all be connected to the national grid. Okay, but of course, in this concept that I'm describing to you, the one that was filed in 2014 is not yet implemented in India. In India, there is no penalty based wind forecasting yet. So this is still in terms of industry, in terms of applying this technology, it is still very new in India. Okay, very new means it has not yet been formally or as a wind farm, this technique has not yet been applied in India. So what it is that these two wind farms are connected to this utility grid, and they have their own battery energy storage systems, and a centralized controller is monitoring all of this. Whenever let's say I have surplus wind speed here in this wind farm. Surplus means more than what equivalent to the power that I have. So more than that, if I promise something that promised power is equivalent to, let us say, 10 meter per second wind speed. And right now I have 13 meter per second wind speed. So 13 meter per second wind speed will generate more power. So this surplus wind power that I am generating, I will give 10 meter per second equivalent power to the grid, and 3 meter per second equivalent power I want to save to the battery because it is surplus, right? And let us say this guy has 15 meter per second wind speed. So this guy had 10 meter per second, and sorry, this guy had 13 meter per second. I had promised 10 meter per second, so 3 meter I'm saving here. Let's say this guy has 8 meter per second. Okay, now he cannot save, he has to take from the battery 2 meter per second, equivalent of that, and then give 10 meter per second. Let us say he also promised 10 meter per second to the utility. So the 13 meter per second guy and the 8 meter per second guy both have to deliver 10 meter per second or equivalent power corresponding to the 10 meter per second to the utility because they promised that. Is that clear to everyone? Okay. So I'm audible, right?
Yes, sir. Yes, sir.
Yeah,
Continue.
Yeah. Okay. So I both wanted to deliver 10 meter per second, right? Let's say at 6:21 p.m. This guy has 13 meter per second wind speed. This guy has 8 meter per second wind speed. So both have to use their battery because this guy has surplus and this guy has shortfall. The surplus guy will store in the battery. The shortfall guy will take from the battery. So there is charging and discharging taking place in both their wind farms, both their batteries. Consider a different scenario. Consider a situation where it was same 10 meter per second was promised by both of them. This guy has 13. So what he will do, he delivers 10 because he promised 10, right? The remaining 3 he has. This guy had promised 10, but he has 8. So this guy can deliver to the utility on behalf of this farm. How much? He can deliver 2 meter per second to equivalent to that to the utility on behalf of them. So both of them have delivered how much? Equivalent to 10 meter per second wind speed. They have delivered to the utility. The utility is happy. This guy has 13, right? So 13 minus 2 and minus 10. So he has 1 meter per second wind speed equivalent power surplus. So he will store that in the battery. So you will say, sir, what is the difference? This guy had 13, that had 8. They both have to give 10, but this guy gave 10 and this guy gave 8 from the wind speed and 2 from the battery. He too can give, and this guy stored in the battery. But in the first scenario, this guy has to charge the battery equivalent to 3 meter per second. This guy has to discharge the battery equivalent to 2 meter per second. Whereas in the second scenario, there is no charging or discharging in this case, and only a charging of 1 meter per second equivalent in this case. Is it clear to everyone? This difference, is it clear to everyone? I think 91 people are here. I hope this difference is clear to you. Only then it will make sense to talk about further more complicated things. I need some validation from someone.
Yes, sir. Yes, sir.
Okay. So this 1 meter per second equivalent only I have stored in the battery. Why? Because this guy had +3, this guy had -2. So we did the mathematics or arithmetic, 3 minus 2, and 1 I used, for 1 only I used the battery. So usage of battery is less. You will soon see that battery is very critical. I will show you with actual statistics that the usage of battery, if you minimize, you are the king. You will have more AEP, or the annual electric power that is generated from the wind farm will be more. Okay. So this is the concept, very simple concept. Okay. This helped save us at GE in the year 2015. It helped save us 700,000 US dollars from one wind farm in Munich. This concept, okay, which had GE 5.2 megawatt wind turbine. This one simple concept helped us save 700K US dollars just from one wind farm that GE was operating. Okay, so I will talk about the turbulent waves concept when I get to it. Okay, I will now, for ease of understanding, I will not read all of these. I will talk with this picture. Okay, so in this talk, we are going to do, I said, three things. One is wind forecasting. The second concept is the decision making, and the third is wake management. And we will try to remain in this integrated region to provide the integrated solution. Okay. So these three things that I spoke to you in the very beginning in the slide, this overview slide, these three things we will do, and then we will find the integrated solution. So let's start with wind forecasting. So objective one is hybrid machine intelligent forecasting. To do this, we use wavelet transform, okay, and Dabash's DB4 wavelet filter. Okay, these are the fundamental parts of this, but we use some machine learning techniques called support vector regressor and 4 variants of this support vector regressor. Why you use machine learning? You may ask, sir, why don't you use deep learning? That would be a very good question, but the answer is also very simple, that in wind is very random, and wind is not because of the highly random nature of wind, it doesn't help to have a very large data set. See, data sets are collected, or the wind speed is collected at each 10-minute window. At each 10-minute window. So every 10 minutes, there is a dispatch. So if I take a data set of, let's say, 1 month old, it will not have any relevance. So statistics have shown us that about 1,000-1,500 data points are good enough. You don't need 1 million data points. In fact, that doesn't help. And also machine learning algorithm, supervised and unsupervised machine learning algorithm have been very successfully used on 1,000, 1,500, 2,000 data points. For deep learning, you need around at least 15,000 data points. So, or to actually see much difference. And in fact, if you start using deep learning techniques on like CNN or something on this kind of 1,000 set data points, you will get worse results. Okay. So we have used machine learning techniques like support vector regressor, SVR. In that 1,000 points, we are using 800 points for training and 200 for testing. So we do this on 4 wind farms. This A, B, C, and D, which are given over here. The wind farm, the first wind farm is in Sotavento in Spain. The only reason for taking this is that they are giving data freely. You can right now type Sotavento wind farm, Spain. You can go to their website. You can see what is the current wind speed and all the other statistics, the density, whether there is any wind variation due to rainfall, humidity, all these things you can check. Means the data is freely given, available for anyone. The 3 other wind farms are in Massachusetts in US. The reason I am taking these 3 wind farms is because they are nearby, because they are all in one particular state in the United States. And so our technique that I showed you over here, this technique we can apply when I use these three data sets from Paxton, Blanford, and Bishop and Clark's. Okay, so this is the only reason why we have taken these four data sets. I will show you subsequently in the presentation that we are taking many other data sets of we have 6 other data sets, out of which 3 are onshore, 3 are offshore. Offshore means where the wind farm is actually in the sea, okay, not on the land. And then there are wind farms of in Australia and in Tibet. So we have covered a large variation or a large type of geographical varied locations which validate the conclusions that we have made. So for these 4 data sets, we compare the error statistics, the root mean square error, mean absolute error, some Thiel statistics. Okay, so these are very standard statistics that are used in analysis of any forecast that you do. Forecast means what? Right now, I am telling what it will be or what a parameter will be after half an hour, let's say, after 15 minutes, after 10 minutes. And then when that time comes, I will check what is the actual wind speed and what I had predicted. And between that, I will find the error. So like this, if I find the error for all the data points and then do this root mean square error, you know what is root mean square error means. Okay, so the square root of the mean square, okay, of the error. That's all. Okay, so like this, there is mean absolute error and all these other statistics. So for the analysis of this on this data set, we have used 4 variants of support vector regressor. Epsilon SVR, least square SVR, T or the twin support vector SVR, or epsilon twin support vector regressor. So now I want you to, because all of you may be from very different backgrounds, you may not be from wind forecasting or wind farm background, you are not working on that or researching on that. So I'm not talking about the very specific mathematical aspects of this. But conceptually, I think everyone can understand. So in general terms, let us try to understand this. Now there are 4 variants or some variants with some small differences in their mathematical structure. Okay, but they are all support vector regressors. I have taken 4 different variants. But then there is this 5th one called persistence. What is persistence? See, if I take a machine learning algorithm and then just apply it and show you that, yes, see, this is doing good and all that, you may always question that why have you chosen this method? Why not this one? Why not that one? Right? So I will also compare these with 2 other techniques called random forest and gradient boosted machines. Soon I will show you. But I should also compare with something very simple, which is not a machine learning technique at all, which is called persistence. What is persistence? Persistence simply means that right now it is 6:33. At 6:33, I can predict what is the wind speed at 6:43. And then when 6:43 comes, I will find the error between the actual one and what I had predicted 10 minutes ahead of time. Like this, I can find for 6:53, 6:73, 6:63 means 7:03, 7:13, 7:23, like that. So let us say I did like this for 20 different data points, 10 minutes spaced apart, right? So what is persistence? Persistence simply means you find out these errors of last 20 samples, add them up and take average and say that that is the forecast for the 21st point. Making sense? To predict what is the value of wind speed 10 minutes ahead of time, just go back 20 data points, find the error in all of them because it is in the past, so you can find the errors, add them up, divide by 20, you will get the average, and say that in 21st point, just blindly or stupidly, just say that the 21st point is simply the average of the last 20. That is called persistence. Now you may say that that is a very, you are yourself are saying it is stupid. Then why are you doing a stupid technique? Because if we say that there is some machine learning algorithm that we are using, this is very good and that and all, it should at least do better than persistence. Of course, we are comparing multiple of them and not just only one and picking that. But whatever number I may do and glorify it as machine learning technique, it should do better than persistence. I think everyone will agree. And so I must compare them with persistence as well. And of course, if you do that, you see the ridiculous difference in them. For example, the root mean square error in epsilon TSVR is 0.0823 and in persistence is 0.7241. So in persistence, the root mean square error is almost 9 times less than, in epsilon TSVR, it is 9 times less than persistence. In TSVR, it is almost 36 times or 35 times better than persistence. Along with that, we also check the CPU time. Okay, now when we first started doing this 7-8 years ago, CPU time was still an important attribute. Now people are more and more not bothered about this because they have all techniques are very fast. So CPU time is not really a very much of a concern. Okay. At that time also it was not that much of a concern. All of them were equally considered equally good. Still, if you want to make some small observational difference, you see that the least square support vector regressor is the best in terms of CPU time. But in terms of RMSE, in terms of MAE, the TSVR and epsilon TSVR are better. Okay, so we make these conclusions. In terms of overfitting, also epsilon TSVR and TSVR are better. Okay, so then there is something called as robustness of the hybrid model. There is some math here in the next 2 slides, but I just want to, without getting into this math, I will just simply tell you what does the meaning of robustness mean. Robustness means that I have taken these 4 data sets, and done some conclusion. Okay, I have found that epsilon TSVR and TSVR is better, is outperforming in terms of RMSE, in terms of LSVR, the computational time is, in terms of computational time, LSVR is doing better, in terms of overfitting, these are doing better. Now, if I take some other data set, or I take this data set after 5 days, again I collect the data, and now I again do this exercise, I should get something similar, not very drastic, not something 180-degree apart. If I get something similar, then I will say that my model is robust to any uncertainties, robust to changes, means my model is reliable. Okay, so the simple language, layman understanding of this complicated stuff is that the robustness of the hybrid model is considered good if it is unchanged when I change the data set. Okay, or if it is minimally changed when I change the data set. Okay, so this is forecasting. Okay, so I took a data set from these 4 wind farms and 1000 data points, and then I found which machine learning algorithm is doing better. And of course, they did all much better than persistence. I found among them which of them are doing better. And I also checked that the robustness of the model is there for all the 4 data sets. So we are happy that not only the forecast is good, it is also robust. Okay. So that is our first step, or the objective 1 is fulfilled. Okay, but I don't want to be here. Okay, I want to be here. Okay, I want to do wind forecasting, decision making, and wake management, all 3 on the same data set, right? So for decision making, I will do the following. Okay, so I will come straight away to this. So see, decision making is not something we invented. It is applied in supply chain management for last 60, 70 years. Forecasting technique, machine learning techniques are relatively new. Okay, last 15 odd years it has been used. But multi-criteria decision making or decision making itself is not very new. But its usage in the kind of problem that we are using, that is very new. Means that was we used it for the first time. So what we are doing here, we have identified 4 alternatives. Okay, so please carefully pay attention here. What are the 4 alternatives? Okay, so there are 4 alternatives. The alternative one is that whenever there is a shortfall, so I have a wind power generated PI. I means ith forecast window. Okay, the wind power that is generated in the ith forecast window. Let's say there are K dispatch windows or forecast window. Okay, TI is the total that I am counting by adding all the differences, right? But let us say PI is the power generated in the ith dispatch window, and P hat is the estimate of the power. Okay, so I have to predict ahead of time, I told you, right? So prediction and the actual, I will find the difference and then add all the differences for the total number of dispatch windows, which is K, and B is a weight that I have given to this total forecast error. Okay, so that is the penalty that I have to pay for making a forecast error. Okay, so if I pay for every penalty, if I have a strategy that I will pay for every penalty, then I am going for alternative 1. Making sense? What is alternative 2? Alternative 2 is pay penalty for using battery up to a certain threshold. That means you identify a threshold power, PVTH. And if your wind power is more than the estimate, that if the difference is where the difference of that is the threshold, up to that threshold, you use the battery. After that, don't use. Means don't do deep charging or deep discharging. Okay. So use battery, but also pay penalty for the difference. But don't, to escape paying penalty, don't use entirely the battery. Okay, this is an alternative. We'll test whether this alternative is better or not. Okay. First one was alternative 1 was don't use battery at all. Always pay penalty. Alternative 2 is, please pay attention. There may be a quiz at the end of the lecture. Okay. So alternative 1 is pay penalty for every forecast error. Alternative 2 is pay penalty up to for using battery up to a certain threshold. After that, use the battery. So alternative 2 is a combination of battery usage and paying penalty. Okay. What is alternative 3? We will test all these alternatives. Okay. So just hold on. So alternative 3 is what? Alternative 3 uses our patent technique, which we described to you over here. Okay. So what is alternative 3? Alternative 3 says that pay penalty for borrowing deficit power from neighboring wind farm. So I will borrow from the neighboring wind farm. Let's say there are 3 wind farms. In this case, I'm taking. Okay. So if I need from the neighboring wind farm, I have a shortfall. I will take from the neighboring wind farm. I will take from the neighboring wind farm and deliver to the utility. Okay. So there are 3 wind farms. So if wind farm 2 can give me, I will take from there. If wind farm 3 can give me, I will take from there. So if you have more such wind farms in your this network, we found that if you have 3 or 4 wind farms, then almost you will not have to pay. Typically, you don't have to pay penalty because one or the other will have the ability to give you the power or the deficit power. So this is alternative 3. And what is alternative 4? Alternative 4 means that pay penalty for deficit power using entirely from battery. Means pay penalty, everyone has to pay penalty somehow or other, either to the neighboring wind farm or usage of battery, or actually paying money to the utility because I don't want to use the battery. So first one was that, directly pay penalty to the utility. The alternative 4 is you use the battery all the time. Don't give any money to the utility for penalty. You consume the battery all the time. These are 4 alternatives. So what are those 4 alternatives again? Recap. Alternative 1 is always pay penalty. Don't use battery at all. Alternative 2 is up to a certain threshold, you pay penalty and then use the battery. Alternative 3 is you pay penalty, but that penalty is not paid to the utility. You do leverage your network. You ask your neighboring wind farm to cover your shortfall. He will deliver your power to the utility. Okay. And so in this case, we'll see which is the best. The alternative 4 is what? In this case, we don't pay anything to the utility at all. We simply, like alternative 3, we will pay penalty to the utility only when any of the neighboring wind farms is unable to provide us or provide on behalf of us. Whereas in alternative 4, we don't pay any money to the utility. We consume the battery entirely. So which one is better? We will test now. Okay. So to do this, of course, we did this on these 3 wind farms in Massachusetts. We also hypothetically tested it on an Indian site. Okay, there is no such wind farm which is applying this technique in India. Let me clarify again. There is no such wind farm in India which is applying this technique, because wind farms in India don't employ batteries to charge or discharge and then provide the shortfall to the utility, because in India the model is whatever you are generating, you simply give to the utility and utility will give you money on a monthly or yearly basis. But wind speed can be measured, right? If you measure the wind speed in 3 different locations, you can calculate what will be the equivalent power if there was a wind farm. And if this technique was used in India, and we have a national grid where if we pump on behalf of each other, these wind farms, and employ these 4 alternatives, what will happen? That we can test. Okay. So we did that. And we'll see what is the result. So these are general functioning methodologies of multi-criteria decision making. I will not get deep into that. If there are any questions, I can come back to these and explain in depth if anyone has any questions. What I will do is I will now talk about 3 different techniques of decision making called SAW, TOPSIS, and COPRAS. Okay. And they employ some different metrics, different calculations. Okay. These calculations are here, but we will not spend time talking about what they are. Okay. But we will compare from the data that we get. Okay. So I will come directly to this slide over here, where I am making decisions based on 3 different techniques: SAW, COPRAS, and TOPSIS. And what do we see here? We have the 4 alternatives: A1, A2, A3, A4. We have ranking 3, 2, 1, and 4. What does it mean? It means that A3 is found to be the best. A3. What is A3? A3 is Alternative 3, that is pay penalty for borrowing deficit power from neighboring wind farm. Engaging neighboring wind farm is most beneficial. This we found in all these data sets. We found in the Munich wind farm on which we worked while I was at GE, which led to 700K US dollar profit in terms of annual electric power output of that one specific wind farm of 49 wind turbines. One specific wind farm of 49 wind turbines. Okay. All right. Just from one specific wind farm. Okay. And we find that now for all these three techniques, just please focus here, this slide, just here. Okay. See, for all these three techniques, the ranking remains same, 3, 2, 1, 4. These four alternatives. The best is A3, which is usage of borrowing technique from neighboring wind farm. The second alternative is use battery up to a certain threshold, that one. Okay. The third one is paying penalty to the utility. And the last one is paying, means use your battery, don't pay penalty. What does this slide tell us? And this is the slide why I have chosen this topic for today, even though Praveen had requested me to speak on battery and these things of hybrid electric vehicles. Okay. You can see, and I believe I am talking about this concept because the usage of battery is so critical. You can see that using battery is found to be worst than paying the penalty for wrong error forecast. See, paying penalty of wrong error forecast is a huge cost. You have to pay in a large wind farm, you have to pay like 6, 7, 800,000 US dollars penalty every year to the utility for forecast error. But even that is better than using your battery like crazy, like deep charge, deep discharge without bothering about anything. If you simply use battery, that is not a good idea. This data tells us. So battery management, battery life management is very, 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 how many ever very I may use. It is not too much. It is very, very important. Okay. So what we have found so far, we have found that TSVR and epsilon TSVR are very good in are very good machine learning techniques for forecasting. We have found that using neighboring wind farms for supporting us when we have a forecast error is very good. Okay, is the best alternative. Okay, rather than always paying penalty up to a certain threshold, or always using the battery. None of them is better than using or collaborating with the neighboring wind farm. Okay. But that only covers up to objective number 2. What was objective number 2? Decision making. Objective 1 was wind forecasting. So we have done this, we have done this. So we have done this part together. If we do both of these, that means we are here, right? But we want to do more. We want to enhance the life of the battery storage systems. Okay. And for this, we need to understand a very important concept called wind wakes. Okay, so imagine, okay, I believe all of you are nationally from many different parts of India. Okay, I can see you are all from many different parts of India, but let us take example of Chowpatty Beach. Okay, Chowpatty Beach in Bombay. Imagine there is a wind turbine which is right at the Chowpatty Beach in Bombay. Okay. And this wind speed, this wind speed V naught, free stream velocity, is coming from the Arabian Sea. Okay, there is no obstruction. It is called free stream, means there is no structure here which is blocking this wind speed. Okay. In Bombay, in the Marine Drive and regions like that, there may be some structure which is blocking. Okay. But you assume that you are in a certain section of that Chowpatty beach where there is nothing which is blocking. Okay. So if this is the free stream velocity and there is no blocking, and now you think that this is your wind turbine 1, WT1. This is getting this free stream velocity entirely, no reduction. Okay. Then what will be the wind power generated by this? There is a cubic formula. Okay, where this is proportional to the cube of V naught. Okay. All right. Now, but what about the wind speed or what about the power generation capability of WT2? Is it also V naught, that is be the free stream velocity? No, because this is downwind turbine or downstream, it is called, because this is unlikely to see this free stream velocity V naught. Why? Because typically the distance cannot be very high. If it is very high, you will need lot of space, land, valuable resource to put your turbines. And land is very scarce, so you cannot put really very far apart. So typically a good distance is 4D. 4D means 4 times the diameter. This is the turbine blade, this is the turbine blade. So the diameter of this turbine, if it is D, then this distance is 4D. Okay, so 4 times the diameter. 4 times the diameter is required minimum for you to be apart, so that you will not get, so that you will be able to get the wind speed and which is not reduced. Okay, wind speed will remain V naught. Okay, if it is more than 4 times diameter. If it is less than 4 times diameter, there will be a chance of reduction in wind speed. But imagine these are very large turbines. This 1D is very large. Keeping them 4D apart is 4D is minimum required. In most terrains, 4D is also not enough. 5, 6, 7D is required. Okay, for you to get entirely V naught. So typically, it is not possible to get V naught for this wind turbine WT2. Okay, why? Because this turbine faces backwind from this turbine or upwind turbine, and that is called wind wake. Okay, the reduction in wind speed seen by this turbine, the downstream turbine, as a result of the presence of the upstream or the upwind turbine, is called wind wake. We found that if I use yawing of this turbine blade, of the yawing of the upwind turbine, that's why I have shown this turbine blade again with this gamma, okay, yawed by a certain angle. Okay, so I think I want to show you what is yawing. Maybe some of you may not know what is yawing. So let me see if I check my, yeah, my video, and I hope you can see my hand. All of you can see my hand. Please confirm. Everyone can see my hand, extended arm. Someone please confirm.
Yes, sir.
Okay. So I want to show you what is your role and pitch. So that you are absolutely clear what I am doing to the turbine blade. Okay, so imagine this is my arm, this is an aircraft structure, okay, aerofoil. What is roll? Roll means this. This motion is called rolling. Okay, as if like a cricket bat or a baseball bat is rolling on the ground like this. Okay. Okay, this entire arm is rolling like this. This is called roll. Okay. This is roll. Okay. What is pitch? What is pitch? Okay. This motion from my here, this motion I'm showing, this is called pitching. Okay. This is pitching. This is rolling. This is pitching. Okay. And what is yaw? This motion is called yawing. Is it clear to everyone? Is it clear to everyone? Now I'll start taking some names. Tipiri Setti Rakesh ji. Tipiri Setti Rakesh ji, can you please confirm if it is clear to you? Am I audible to you, Tipiri Setti Rakesh? Vimal Moore ji, can you confirm?
Yes, sir, I understand.
Okay. Okay. Thank you. Thank you, Dr. Moore.
Thank you, sir.
Thank you, Dr. Moore. So that is yawing. Okay. So yawing by, we find in this work that yawing by 5 degrees. Okay. Yawing this turbine blade or modifying the yaw angle of the turbine blade by 5 degrees reduces the wind wake that is created on the downstream turbine. So if I yaw the upstream turbine by 5 degrees, I can keep the downstream turbine 4 degree or even less, 3.5 diameter apart and still have full wind speed, free stream wind speed available to the downstream turbine. Okay, and we check and we find, I'll come back to this battery energy model, but I want to first straight away take you here. So when there is no wake effect, of course, your position is not required to change. If I don't want to do your wake management, I don't have to change the yaw position. But when I want to do wake management, that is case, so I'll compare case 2 and 3. When I want to do wake management, the yaw position is changed by 5 degrees. Okay. So, and I test it. I told you that we'll test our work on multiple data sets. So that will prove the robustness of our study. So we are checking in two data sets which are different from what we have done so far. So there is a wind farm site in Chelicum and another in Longyuan, Tibet. And we have tested this yawing model on these two data sets. And what is the result? We find that when the battery energy storage system rating is, we checked it at 3 different kilowatt hour of battery. But we find that in all of the cases, for both case 2 and case 3, in all of the battery size, okay, the percentage of saving in life cycles is at least 5%. You can see this is Chelicum data set and this is long one. At least 5% benefit we are getting in battery life cycle saving. Why it is important? Because we already saw that battery life is most important. Among the 4 alternatives, using recklessly the battery is found to be worst. Okay, so in that case, saving of battery life cycles is very important. And by yawing, we are able to save the battery life, that we are demonstrating over here. Okay. Compared to means saving means what? Case 3 is at least 5.31% better than case 2. Okay, if you have 1000 kilowatt hour battery. If you have a smaller battery, then the saving is even more. Obviously, that makes sense, right? Because if you have smaller battery, you will reach the threshold faster. So if you are saving battery, the percentage of savings will be more. Okay. So what we have proven? We have proven that yawing the turbine blade helps us save battery life. Okay. So these three things, if we combine into an integrated solution, and I am like, for example, here I am formulating an integrated solution where J is the error in the forecasting. J is equal to 1 is error in forecasting. J is equal to 2 is battery threshold exceeded. J is equal to 3 is deficit power borrowed from neighboring farm. And J is equal to 4 is deficit power supplied from battery storage. So the same four alternatives. Okay. If we take them and find an optimal cost of this, then we see, and I'm not focusing on the battery state charge algorithm and things like that here. I can take this as part of any questions that you may have. But you see, I am going to compare, I'm going to show you with a data set comparison, actual data, that even if I just simply add the benefits from the three different cases that I showed you, the integrated solution, I will still be able to decipher or find an optimal solution. So to do this, I'm taking again, how many data sets we have shown so far? 3 data sets in India, 3 in Massachusetts, 1 in Sotavento in Spain, 1 is Jellicum, and 1 is in Longwan in Tibet. Now I am taking 6 more data sets. Okay. 3 of them are in offshore turbines and 3 on onshore. Offshore means in the sea. Okay. Onshore matlab on the land. Okay. So what happens? So I'm checking cost V1. V1 is the first case or forecasting cost. Okay. Or objective 1. The first Venn diagram. Okay. So I'm comparing now these 4 methods. Why I'm comparing these 4? Because I have already compared, I've already found that among the 4 support vector regressors and persistence, these are the 2 best methods. So I'm taking the 2 best support vector methods and persistence. Among the 5, I'm taking the best 2 and then comparing it with random forest and gradient boosted machines. When we were doing this, one reviewer asked us, why don't you compare with random forest? Why not gradient boosted machines? They are found to be very good techniques. Yes, they are good, but in wind forecasting, we didn't find them to be very good. And the data proves it. Our TSVR is much better than any other technique, as you can see over here. And this is not the case only for one wind farm. For all the 6 wind farms, both onshore and offshore, shown over here, the TSVR outperforms all of them by a very large distance. Okay. So that's a very, very great, there is a very satisfying check. Okay. For the second case, okay, of the 4 alternatives. And in this case, to show you really this very carefully, you should, if you observe, I'm going to expand this size so that you can see nicely. So this is cost V2, the second one. And I'm just taking one of the wind farms here. Okay. I can't even pronounce this very well, but this is one of the wind farms. What I want you to focus on here is, see this graph. Okay, the expanded version, one of them. Everything actually has the same trend, but this is easy to see. So I'm asking you to focus over here. Here, this is cost. It reduces till 0.8. Okay. After 0.8, it slightly increases. So that means this is at 0.8 threshold is the optimum value. Okay, this is the same for in all the cases, but just say यहाँ पे you may debate that no sir, it is not increasing, it is remaining flat. But actually this is also minimum point is here only. It is just that it is not very easy to see. Here it is little more easier to see. There is a slight slant over here. Okay, in all the others also it is there, but it is not very easy to see. Okay. But what does it mean? It means that there is a minima at 0.8. Okay. If you put the threshold above that, then your battery battery life will be diminished very fast. And that is what we also know, right? Sometimes nowadays, laptop batteries also have an automatic disconnect inbuilt in it. Even there are software programs which will do that. Automatically does it. Because if you have plugged in your laptop in like 5-6 years ago also, this problem was there that there is no such switch off. So the when it is plugged in, it tries to charge. Okay, continuously it tries to charge even though it is already fully charged. So that also reduces battery life. Practically, we have seen this, tested it. Okay. But here I can see we can see that 0.8 is the threshold. Beyond that, if you go, it reduces battery life again. Okay. So now let me again come back to the original size of the So V2 is found minimum for at 0.8 threshold. Okay. What about cost 3? In cost 3 also we check that for all the 6 wind farms, again, we find that TSVR and epsilon TSVR are again better. Cos 3 means wake management when I do the 5-degree yawing. Okay. So again, I find that these give me minimum. Okay. And graphically, you can see here, this is a clincher. There is no more after this. There is no debate anymore because all the 6 wind farms are here. The number of distinct battery state charges. What does it mean, distinct battery state charge? I want to again ask a question. Let me ask someone. Let me check whether actually people are present. Rubina, are you there? Rubina ji, are you there? Are you able to hear me, Rubina ji? Yogesh Dabhole, are you there? Yogesh ji, are you there?
Yes, sir.
Yes. So Yogesh, please answer one question for me. Are you able to see this slide?
Yes, sir. Yes, sir.
Yogesh, please tell me what is the meaning of number of distinct battery state charges? See, charging and discharging is taking place in the battery, right? Every dispatch window, charging and discharging may take place. Small amounts, large amounts, but it may be there. Okay. If not in every dispatch window, in specific windows, in some dispatch windows, let's say there is no charging or discharging because I borrowed from the battery, I borrowed from the neighbor or paid the penalty. Okay. But let's say at 7:13, I have charged the battery with some small amount because I had surplus wind speed. At 7:23, I may not do anything like that. At 7:33, I have again charged. So if on 2 different consecutive windows I have charged, what does it mean? How many distinct battery charge has happened? Yogesh ji? Okay.
Can you, sir?
I'm saying, what is the meaning of distinct battery charge? What does it mean? Number of distinct battery state charges. What is the meaning of that? Distinct word पे focus करिए. What is the meaning of distinct battery state charge? Okay, let me explain. When you have, let's say let's say now it is 9:14, sorry 7:14. At 7:14, let's say I have done charging. At 7:24, if I do discharging, then charging and discharging together, one cycle is complete. Okay. So number of distinct state charge cycle is 1. If at 7:34, I charged at 7:14, at 7:24, I did discharging. At 7:34, I again did discharging. Then state number of distinct battery state change has not taken place. Okay. At 7:44, if I again do discharging, again state has not changed. If at 7:54 I do charging, then state has changed. Are you following?
Yes, sir. Yes.
So here this number shows number of distinct battery state changes. So if I am changing the battery state of charge, means charging, then discharging, then charging, then discharging, then every time there is a state change. If the state doesn't change that much, then it is good for battery life. Okay. And we see
Yes, sir.
that using TSVR, the number of changes in battery state is very less. Okay, this is a cumulative number that you see. So for all the wind farms, the cumulative numbers are shown, and TSVR again does very well. Okay. So, and here I show that for this threshold, what is H1, H2, H3? If you have not noticed, it is here. So these are the weights given to the three cost matrices V1, V2, V3. I'm just giving some weight H1, H2, H3 and to calculate. It is not the best way of optimizing, but here in this work, the focus was not on optimization. The focus was on finding an integrated solution. You can use optimization technique or meta heuristic optimization technique to improve this further. Okay. So if I proceed, what I have done here. I have found that there are two weights. Okay, H1 and H3, if I take them even one, and H2, H2 is the threshold value. If I take it as 0.4, I get these numbers. Again, that is best. If I take H2 as 0.75, I get them, the numbers change slightly, but still TSVR is again the best. And if I get these three weights and simply add the three values V1, V2, V3, it is also a cumulative metric. Okay. I can use an optimization algorithm to find H1, H2, H3 and find a better cost metric. But this is also or still a workable solution. So this is actually what I wanted to communicate. I take you to this concluding slide where basically what we have done, we have found that TSVR is the best for all the data sets. We have found that finding a threshold value at 0.8, we found for a farm operator, the economic benefit happens when you operate with 0.8 as the threshold. And if you have the battery health is very significant because we already saw that the decision making technique, multi-criteria decision making technique showed us that that among the four alternatives, using only battery was the worst. So battery life is the most valuable resource. In this work, one can do further work based on the terrain of the wind farms that will have some forecasting challenge based on the terrain. Predictive analytics of turbines, for example, the turbine blade, there may be a crack or ice may have been deposited and some things like that. That can also be taken into account to make this prediction. Okay, so all of these affect battery life. And if this shows you can have this kind of data set to apply batteries used in any application. Okay, so usage of battery has to be optimized, and or battery has to be used very judiciously because battery life is most precious resource, more than even paying penalty for making a forecast error. So that is where I will end, but there are certain aspects which I didn't focus for want of time because I wanted to also save some time for us for questions. So over to you, Praveen. I would be happy to take some questions at this point. Am I audible, Praveen or Vaibhav?
Yes, sir, you are audible.
Yes, sir. Yes, sir.
Dear participants, if you have any queries, any questions, you can just unmute yourself and raise the queries.
Sir, we have one query. If
Yeah.
wind farm is grid connected and
Yes.
battery storage is not used, what is your opinion?
If wind farm is grid connected,
And we are
and
not
that
using the battery is not required in that case.
yeah, so
Whatever fluctuations grid will absorb. Then
no,
what will be the
no,
your
no,
opinion?
no. It is not like this. Uh, if wind farm is not if batteries are not used and wind farm is connected to the grid, see, wind farm is connected to the grid even in India also. Wind farms are
Yes.
pumping power to the grid. Okay, battery is
Yes.
not there.
Hmm.
But in India, the way it works now is like this. Imagine right now there is 15 meter per second wind speed. Okay.
Yes.
Equivalent wind power will be calculated and that wind power will be delivered to the grid. Okay.
Grid.
Whenever, whatever I am generating, I am giving to the grid. Right. I am
Yes.
not
I'm not
guaranteeing anything.
guaranteeing anything.
I'm not guaranteeing anything. So
Yes,
when
yes,
I'm not
yes.
guaranteeing anything, I'm simply giving. So that model,
Yes.
if it is till the time that model is there, it is okay. Means there is no penalty because the model, its agreement
Yes,
itself is like this. But in most
yes,
parts of
yes.
the world, the agreement is not like this. Because
Okay.
today, when you give wind power directly to the grid is taking it
Hmm.
or accepting it because they also have other ways of generating or getting from other sources also they are getting power, right?
Yes.
But if they want to rely on wind power exclusively, then this is not, this solution will not work because you cannot say that today is IPL match, but if wind
Okay.
power is more, then I will
Hmm.
telecast. Otherwise, I will not telecast, or I will not,
Okay.
means there will be load shedding, right? So
Okay, sir.
yeah, I see some questions in the chat box. Can I take those questions, Praveen? What is the concept
Yes, sir.
behind PS and CPS? Okay, so okay, let me take you there. Okay, so this is a mathematical part of this work. So let me take you here. Yeah. So this is a calculation. I don't believe I have put the formulas over here, but these are scores basically. Okay, these are scores for these techniques. Okay, this is CPS is cumulative priority score. This is priority score. This is cumulative priority score. Okay, so these are some mathematical number using entropy. Okay, accumulation of that. Okay, accumulation of this error. Okay, this the formula for the error is given. A cumulative or priority score based on this is given. That formula is not there written here, but I can share it. Is there in my papers. I can share that formula with you. So it's a priority score and cumulative priority score. Based on this, okay, whichever is more in this will be considered a better alternative. So you can see the among these the maximum is in A3. So that's why it is considered highest. These numbers are not same in all techniques, but the order is same. The ranking is same. Okay. So that's the answer to your question about CS and CPS. Okay, Dr. Jayashree. Uh, I can share with you through Praveen. I can share with you my papers, which has more details about this formula. Is persistence same as moving average? Yes, persistence is moving average because as the next 10 minutes comes, it is the moving average. Persistence only different, actually exactly same, but in when you assign moving average with a certain dispatch number, let's say 20 dispatch windows, that is the moving average or the persistence. Can we get PPT or PDF? Yes, at least for my session, I will share my PDF with Praveen, and they can decide based on their policy. They can share uh, at least my slides. They can share with to anyone in the workshop. Are there any? Are there any other questions? How can we get real-time data? Is it accessible for anyone? Yes, real-time data for Sotavento. I have not checked in the last 1 week or so, but let me just check. I have a few minutes. So Sotavento wind farm. Okay, let me just check. Yeah. So this is. Are you? Yeah, this is the wind farm. I hope you are. Are you able to see my screen? Can someone please
Yes, sir.
confirm? Yeah, so this is the
Yes, sir.
Sotavento wind farm. Okay, for some time I have not checked this, but in this site you will get the data for. See, they give you a virtual tour real time data. Here you can get real time data. Okay, for this. Okay, they may have made some changes of late. Recently I have not checked, but you can see accumulated in last hour. Okay, they are giving lots of different data. Okay, CO2 avoided, so many other things which I have not used. Some of the kinds of data they are also providing. For me, I have simply used the wind speed. Okay, direction is also very important. Okay, so that is another aspect. But when we do yawing, we take care of the directional effect. Okay, so this is the about the Sotavento. If you just type Sotavento, I'm leaving that link in the uh, in the chat box. Maybe Praveen can share this with everyone. Okay, the Sotavento wind speed link is over here. Any other questions? Naveen and Tejal, I have put the link over here. How yawing is established in real time. So, a very good question. Thank you, Dr. Vijay Jayashree. Yawing, yes, see if I do yawing differently every dispatch window as per the requirement, it will be most optimal. If I can use an optimization technique to find out what should be the exact weighing, exact yawing for every dispatch window. But we have not done that. We have simply found that around 5-degree yawing gives us very good result. So in this because see here 3 different techniques we were using. Most of all these 3 were done for the first time. And so integration of the 3 by any simple technique is giving very good result. So means we were expanding the state of the art at that time by a large distance. So we didn't use any technique to calculate what should be the yawing in every dispatch window. But yes, that to get maximum benefit, you should yaw every dispatch window slightly differently. Right now, it may be 4.8 is very good. After 10 minutes, it may be 5.1 is very good, is better. So that's a very good question. And ideal thing is that you do the yawing every this thing. But again, there is some amount of energy consumed by changing the yaw angle all the time also. So you should yaw very frequently only if the benefit that you are getting is more than the energy that is consumed by yawing all the time. Okay, but very good question, Dr. Jayesh. Are there any other questions?
Any other questions for participants? Okay, can we conclude, sir?
Okay, thank you. Thank you so much Thank you everyone for very
Okay.
patiently listening for the last 1.5 hours. I'm very thankful to all the
Thank you, sir.
participants.
Thank you.
Thank you.
Okay. So, sir, we are
Thank
extremely
you, sir.
honored to have a Dr. Dipankar Deb, Professor IIT Mandi, as a today's distinguished speaker. Sir, your session was technically rich and highly insightful for us. The way you explained about the machine learning based wind farm was truly commendable. Your deep expertise, clarity of concepts, and real world example have greatly enriched our understanding and inspired all of us. We are deeply thankful to you for sparing your valuable time and sharing your knowledge with such enthusiasm. A special word of appreciation goes to all the participants who actively attended the session, showed their keen interest, and contributed through thoughtful interaction and discussion. So, thank you all, and I kindly request all participants to please stay connected. Our next session will begin within the next 10 minutes. So please stay connected, all of you. Thank you, sir.
Thank you so much. Thank you. Thank you to all the participants. Thank you to the organizers. Thank you so much. Thank you.
Thank you, sir. Thank you.
Thank
Thank you very much.
Thank you.
Thank you, sir.
Thank you, sir. I think Suresh sir also joins us. Suresh sir.
Hi, hi, Mugunka sir.
Huh.
Yes, sir. I am in the session.
So you are in the session, sir. Shall we start or?
It's up to you, sir. If you would like to give
Okay.
any
Within a
short
1 minute,
break.
we'll start, sir. Within 1 minute.
Okay.
Okay.